today we're going to talk about Newton's second law calculations. And I'm going to break this up into a couple of different individual videos, and then you can kind of watch them together. So you should have your practice problems for this. And so I want to break that up into kind of the notes that go with the front and then the notes that go with the back. So this first video is going to cover the notes that are on the front. So just some basic applications of Newton's second law. And then the second video is going to look at the types of examples that are on the back of the worksheet. So actually going back and using those free body diagrams, finding net force and individual forces, and then using Newton's second law. So think of this as the intro video and the second video as not the extension, but really the application of what we're talking about here. So this one will be short, and then you can knock out those practice problems on the front and then switch to video number 2 and then do the second set of practice problems. So our title today is Net Force, Second Law Calculations. We're referring again to Newton's second law. And the question that we want to answer is, how do we calculate the acceleration of an object using net force? And I want to start off by restating something that we actually put in our previous notes and that we've again talked about before. And that is a reminder that an object experiences a change in motion, aka an acceleration, only when it experiences a net force. So the next thing is that since we're talking about second calculations, we want to really quickly just redefine Newton's second law. So the first law is about objects at rest staying at rest. The second law gives us our main equation for the unit. So Newton's second law says that the F net, or the net force acting on an object, is equal to its mass times the acceleration. And again, just so that we are clear, Newton's second law only works when we know the net force. So you must find this before you can actually use Newton's second law. So kind of step 1 is always going to be to determine net force. Step 2 is going to be to use Newton's second law. So in our previous notes, we worked on finding the net force. The next sort of piece of the puzzle would be to then figure out, based on that net force, what is the acceleration of the object. So we have force net. Again, that's going to be in newtons. We have the mass of the object in kilograms. So again, if it's not, needs to be. So convert as necessary. And then the acceleration due to the force. So because I apply this net force, this is the change in motion or the acceleration that I get because of that. So again, acceleration would be the change in motion. In really simple terms, because I pushed it really hard, I get a really big acceleration. It goes really fast. So for the sake of practice, go ahead maybe in the left-hand column or just a small space on your notes. We're going to go ahead and write this equation in other ways, right? We have a 3-part formula, F equals m times a, which means we could also use this same equation to solve for or to talk about either mass in terms of force and acceleration, or acceleration in terms of force and mass. So we have that mass would be equal to force net divided by the acceleration, and acceleration would be equal to the net force divided by the mass. So now that we've looked at the equation and we can see it in its 3 different forms, we're going to go ahead and take just a quick snapshot or a short set of notes on proportional reasoning, or those variable relationships. So how does mass and force go together? How are force and acceleration related or connected? All right, so obviously I kind of shrink some things around to fit my purposes, but let's talk about proportional reasoning and variable relationships. All right, so again, the idea with proportional reasoning and variable relationships is just that we better understand really the impact that changing one variable has on other variables. So in this case, we only have a couple to look at. So the first one is force. So we know that force if we look at our equation here, when we talk about proportional, remember we have direct and indirect. So either making one makes the other one larger, or making one larger makes the other one smaller. So in this case, because we have a very basic multiplication equation, we can say that force is directly proportional to both mass and acceleration, meaning that if you increase the force on the object, either it's going to increase the acceleration, meaning it's going to make it speed up faster, or if you have a larger mass, maybe you need to increase the force to reach the same acceleration. And this is something that we're going to look at a little more later on, but just to kind of be aware of for now. We'll practice it plenty before you need to test. The other relationship we can look at is really mass and acceleration. So if we rearrange this equation and we look at the two forms, in this little Post-it note that I doodled, we have m equals f divided by a, or a equals f divided by m. And specifically, we want to look at this relationship. So m to a, or a to m. And we see that in either version of the equation, they are inversely proportional to each other, right? We have one on top in the denominator, or the numerator, sorry, and one on the bottom in the denominator. So we can say that m, or mass, is inversely proportional to acceleration, which again means that if I increase the mass of the object and I use the same force, then it's going to go slower. So heavier objects with the same force go slow. And this is what a lot of you demonstrated in your videos. The other option is that by decreasing the mass, I'm able to increase the acceleration, right? Pushing something light makes it go faster than pushing something heavy. And so these are relationships that we can see and apply mathematically, right? If I double this or if I cut this in half. So on the next page, if you will, I'm going to look at some example problems. This should really fit on one page in your notes, but just some examples of proportional reasoning. All right, so let's look at some proportional reasoning examples. We haven't practiced this in a while, but remember, we're really just looking at if I double something, what is the effect on? Does it get bigger or smaller, and by how much? And Newton's second law is very straightforward, right? There's no halves, there's no square, there's no square roots. It just is either multiply or divide. So the first example, and I'm going to write these out and then kind of talk about them as we go. But if you double the force on an object, then what happens to the acceleration? So if we leave mass alone, if you double the force, what happens to acceleration? So I can look at this a couple of different ways. The first is that if I understand the relationships, then I don't necessarily have to show any work at all. So I know that force and acceleration are proportional to each other because I have force and I have acceleration. So if I double one, then I double the other. So we know just from kind of that basic understanding that 2 times the force is going to give us 2 times the acceleration. We can also look at this in more of a mathematical formula approach. So this is where we would put like blank F is equal to blank M times blank A. And we look at those coefficients. So here, regularly, right, we have a 1-to-1-to-1 ratio. But now I'm doubling the force, and I haven't changed the mass, so it's going to stay at 1. So in order to maintain my 1-to-1 ratio, whatever I do to force is going to happen to acceleration. So I end up with 2a. So however you get to that conclusion. So our next question is if you double the mass but use half as much force, what happens to the acceleration? So now I'm not only changing one thing, I'm changing another. So again, I can look at this from a proportional reasoning standpoint, and it is 2 parts. So the first thing that I did was I doubled the mass. So I have F and M. So I know that if I double the mass, it's going to affect the force. Or if I look at it in this sense, if I double the mass, if mass goes up, then acceleration has to go down. So kind of the first thing I can make is to say that increasing mass is going to cause a decrease in acceleration. And then we're also asked to look at the effect of force. So if we go and look at force, let me switch some colors here. If we look at force, we see that force and acceleration are proportional. So I'm going to go lose a third equation. But we can see that whatever I do to force also happens to acceleration. So in this case, by decreasing the force, I'm also going to decrease the acceleration. So here we have two instances. Both things that I change are going to cause the acceleration to decrease. So I can't necessarily think right yet about how much, or maybe you can. So let's talk through it. So if they're inversely proportional, if you double one thing, the opposite of that is to cut in half. So this is going to cause it to be half as much acceleration. And since force and acceleration are directly proportional, they do the same thing. So if I used half the force, I'm also going to get half the acceleration. And 1/2 and 1/2 get me to 1/4. So let's see if that works using the formula. So now we're going to go blank F equals blank M times blank A. So again, our original ratio is 1 to 1. Right side, left side. In our new scenario, we have twice the mass and half the force. So I need these two sides to balance out. So I have 1/2, and I need 1/2 on this side as well. So 2 times some number is going to get me to 1/2. So again, we look at that and we can kind of divide it over. So 1/2 divided in half again, or divided by 2, gets you to 1/4, which was the same conclusion that we came to over here. So two different ways. I like proportional reasoning because it has you look at those relationships. And then the last one that we're going to talk about is kind of in reverse of that. So we've talked about what we did, and then we figured out how it affected acceleration. On the next question, I want you to try to figure out what to do in order to cause something to happen. So the question we're going to answer is, how do we get 4 times the acceleration? So what do I need to do to an object to quadruple the acceleration? And there's more than one answer. So there's really 2 ways that I can think about it. Option 1 is to try to increase the acceleration of the original mass. So I want to keep the mass the same. So it's the same object. So again, if I think about my proportional relationships, if I want to increase acceleration and leave mass the same, then I need to increase force because they're directly proportional. So 4 times the acceleration means 4 times the force, so 4F. The other thing that I can do is use the same force. So maybe I want something to accelerate 4 times faster, but I'm only a certain amount strong. So the other thing you can do is keep the same force. So in this case, we know that acceleration and mass are inversely proportional. So if I want an increase in acceleration, I would need a decrease in mass. So 4 times the acceleration, the opposite of that, or the inverse, would be 1/4. So in that case, I could use 1/4 the amount of mass. Either of these things, or either of these changes, again, keeping mass, keeping force, would allow me to quadruple my acceleration. All right, I'm going to flip to just one more page. The last thing that I want to do for right now is just do some very basic Newton's second law calculations. So we're actually going to use the example problems 1, 2, and 3 from our net force example. So I'm going to drop the picture in the next screen, but just flip back and look at the 3 examples of net force. And we're going to use those to calculate the acceleration of those particular objects. All right, so we're looking at, again, I just snapshotted these from the last set of notes, so you should have them. We're going to look first at example number 1, so kind of using this as our guide. So the question I'm going to give you is that if mass is 5 kilograms, then what is the acceleration? So if we look at Newton's second law, we have F equals ma, and we have A equals F over m. So in this case, our net force was 40 newtons, so we would have A equals F over m, which in this case would be positive 40 newtons. Remember that positive tells me which direction, divided by 5 kilograms. So in this case, the acceleration would be positive 8 meters per second squared. So to kind of extend on that question, what would happen, sorry, I lost my train of thought. What would happen if instead of 5 kilograms, we cut that in half? So we have half the mass. So we can do this mathematically, but we also just practice proportional reasoning, right? So if acceleration and force are directly proportional, and acceleration and mass are inversely proportional, and I'm asking you to determine the acceleration with half the mass, then we're looking at this relationship here. So we could assume that if you have half the mass, you should get 2 times the acceleration. So if we had 8, then the new acceleration should be 16 meters per second squared. So in this case, we could double check our math. Instead of 40 divided by 5, we would have 40 divided by 2.5, which also gets us to 16. So again, just another way that proportional reasoning can kind of shorten the amount of work that you need to do. On number 2, we had 0 net force. So if there's no net force, there's no acceleration. But just in case you didn't believe me, right, if F net equals m times a, 0 equals mass of, let's go with 5 still, 5 times a, right, a would have to be 0. So mathematically, we've proved our point there. And then let's look at the last one. So here we had our falling object. So just for consistency, we're going to say the mass, it's still the same object, so it has a 5 kilogram mass. Then our net force, which was -5, so acceleration equals -5 divided by 5. And we get that A is equal to -5 meters per second squared. And again, that should make sense. The object is going down and it's speeding up. So we would expect to see that negative acceleration. So a couple of other things, if we were just trying to check our work, right? We talked about the difference between free fall and air resistance. So in this case, we're not in free fall. So we would expect that the acceleration should be less than gravity, or less than -9.8 meters per second squared. And since the upward force is about half of that downward gravitational force, 5 makes sense because it's about half of what we would expect the acceleration due to gravity to be. So just some basic applications. Again, the equation is pretty straightforward. We have 3 versions. F net equals m times a. We used the triangle last time to kind of look at different options. In this case, we would have F is equal to m times a, which gives us m is equal to F divided by a, and a is F over m. So just 3 different ways, again, to find the same thing. So between these notes, you should be able to answer the questions on the front of the worksheet, where you're basically just applying Newton's second law. In the second video, I'm just going to work through some examples. So it will not necessarily be notes, but more a combination of how do I both find individual forces and then get to a point where I can use Newton's second law.